Thank you, Paul. So I hope you can see my slides. So I am Alvin. I am from Institute of Science, Tokyo, and this work is designed to construct data sets of anthropogenic heat emission. And we do this with the help of integrated assessment model called GCAM. So this work is done together with my students. Actually, one of them is here, Jin, and other collaborators from different institutes such as University of Tokyo and Waseda University. So I guess not everyone is familiar in this group about what this anthropogenic heat emission means. So I want to start with that. So when we read some papers, they can be abbreviated as AHE or QF. But where it comes from is from the field of urban climate. So in urban climatology, I'm one of the researchers in urban climatology. Our purpose is to investigate the impacts of humans on weather and how weather affects us humans. So in essence, how the humans affect the climate is related to the energy balance from the surface. So our existence somehow modify the energy balance of the surface that translates to the behavior of the atmosphere. So in a book by Tim Oak and his colleagues on urban climates, so we can think of energy balance like this. So there will be source of energy coming from the sun or elsewhere, and then the surface would respond to that in terms of sensible heating or latent heating, or it may go straight to the ground. But with the presence of cities, it is drastically modified. And then these conditions of the cities, we can parameterize in terms of their morphology or the presence of the buildings or the roughness that can affect how the winds can flow or how the energy is transferred from above to the surface and back. Now, in this energy balance model, there's an added source of energy, and that is what we call the anthropogenic heat. And this anthropogenic heat in the model that I will be presenting is sort of the energy source due to the human activity. So it is the energy derived for the sustenance of life. So they could be energy consumption coming from the buildings, from residential, commercial sources, industrial sources, transportation sectors, or even our movement as humans. They translate as heat released to the atmosphere. So this QF varies in time and space. And there are, I can think of three general approaches to estimate them. The first two models relies on the assumption that energy consumed, it will eventually be released to translated to energy that's released to the atmosphere. And we can derive them based on bottom-up approaches or top-down approaches. So when we say bottom-up, so we do survey of each individual buildings, how much energy they use, and then we allocate them into grids, and then we map them over the region, over space. And we have the top-down models, which I will show in the next slide. And we have actual observation and also models that are embedded in climate models so that it can consider the energy use based on the temperature or even humidity, and then that will be derived as a feedback QF to the atmosphere. So bottom-ups are generally more accurate than the top-down approach, but they have limitations in terms of the frequency or in terms of the area that they have. So along with many other researchers here, and including in my group, we develop global scale data sets based on this top-down approach. So the idea is simple. We have country level or regional level energy consumption, and we find a way, an intuitive way of spatially allocating this energy into detailed spatial distributions, not only in 1 kilometer, but also in hourly time representation. And many of these applications are related to urban planning. In more specifically, in more common applications would be to feed them into what we call regional climate models or even GCMs. And then through this, then we can evaluate, given this amount of anthropogenic heat emission, how much is a climate sensitive to that. That's also an interesting area of research. So why we're doing this, I feel that, or we feel that, when we study or we do climate change projections, we're more in our mindset, we're thinking about greenhouse gas emissions, but actually now the land cover change is drastically happening. So we have cities forming, growing, expanding, population growth, and then leading to urban parameter changes, translating to morphological changes, or even the anthropogenic heat. And this, I think, is not that difficult to understand, that our use of energy directly links us, humans, and climate. So we feel that continuous developments of this estimation would be necessary. And another thing is we develop these data sets, but we struggle to find a time or opportunity to release such models so that other scientists, other researchers can use this so-called top-down global anthropogenic heat model that I will be introducing shortly. So the anthropogenic heat dataset that we're trying to advance is the AH4GOC dataset. So it is publicly available. It has hourly representation, the typical hourly value of anthropogenic heat for a given month. Currently, it has only one scenario for the future and is estimated based on energy levels of the years of 2010s. So it started in 2017, and then we improve it in 2021. And this time, we want to improve it further by coupling it to an integrated assessment model so that we can have a more scenario-driven approach to estimating futuristic QF. So we also want to push forth a toolbox using these open source models and also data sets so that anyone can estimate this QF and feed them into their models. So integrated assessment models. So I hope that everyone is somehow familiar with this. So it gives a quantified estimate of how Earth systems and socio-economic human conditions interact. So the model we use is the Global Change Analysis Model by the Joint Global Change Research Institute from Pacific Northwest National Laboratory. And we are grateful to I suddenly met Dr. Maridi Weber, and she was very helpful in introducing us to this GCAM, which paved the way to connecting this model to our data set. So this is an example of GCAM. So GCAM currently outputs energy consumption and different sectors of this energy consumption across 32 regions, incorporating socioeconomic information, energy technology, policy, and so on. So this is an example of a global map across these 32 regions of final energy consumption. So, and here is our model. It's quite simple. It's a top-down approach from left to right, from the country level, all the way to the 1 kilometer grid level. So we use weights, spatial weighting based on other geospatial data sets that are open source, such as Landscan or nighttime lights data. So from annual total primary energy consumption, we can break down the levels of energy that goes to energy loss, industrial, agriculture, commercial, residential, transport, and then summing them up to annual representative values of QF. And we also have this metabolic heating, which we can empirically estimate from population quantities and hourly activities of humans. So how we try to incorporate GCAM to this is we replace that primary energy, final energy consumption with the GCAM model, and then this will just go into this model. But further improvements are also introduced into this. This includes redistributing the GCAM regions to each country. This part is just an assumption using the energy intensity weighted by GDP. And this GDP could also change with time. And also use other data sets that are consistent with CMIP 6, such as the Wang et al. Dataset for population projections under SSP 1 to 5. And then we also use the downscaled climate model outputs of CMIP 6 consistent GCMs. This allows us to pair the energy consumed from residential and commercial heating and cooling. So we can map better the effects of this use of heating and cooling. So this is just an equation form. So the idea is to get each location's average final anthropogenic heat data. So these are just the breakdowns, and these are actually found in the paper. And these are the improvements by considering the energy consumption due to heating and cooling, and heating degree days and cooling degree days from the other data set of downscaled climate models. And these are the various inputs. So we have the nighttime lights adjustment of population to get us the 1 kilometer resolution point distributions. We get the point source, we get the energy intensity, and we have the GCAM to give us different scenarios of energy consumption. And we have the different scenarios of air temperature that allows us to get the HDD and CDD. And these are just examples of what are the various energy components that we can obtain from GCAM. This blue box is something that we can only derive thanks to the GCAM model. But the current assumption is that we rely on energy intensity, but GCAM also has a function to obtain specific country level values, but this is something that we are still exploring. So once we introduce that, we get some shifts in the QF. For example, this is what happens when we consider more information of heating and cooling. And then we can also introduce other data sets such as road network or road density. So we can get more components specific for transportation, for example. And then finally, we can generate this map across different SSPs at 5-year time spans of anthropogenic heat emission data sets. So this is a total global average anthropogenic heat that is released in the atmosphere under SSP 1 up to SSP 5. But one important advantage of being able to use GCAM is we can introduce policies. So for example, if we have an SSP 5 scenario and we introduce this carbon tax, then we have this amount of global reduction, and this translates to reductions in QF, or this anthropogenic heat, in these locations. These are thermal power plants surrounding Tokyo Bay of Tokyo. So to sum up, so we just introduced GCAM into our model, and we hope that this will enable user generation as open source. And there were some improvements to the top-down spatial weightings that were introduced, but we hope to confirm this more in the future. So bottom-up models are still needed for detailed validation. So further testing, finalizing documentation, publishing, and releasing through GitHub is needed. So how this is being used now? So we have a student who's using regional climate model, feeding our data set into that. We are also working into GCM model, prescribing this data set into the GCM model. And then we also have other works and other collaborators who are trying to improve their building energy models with this data set. So I hope this is just a brief summary, but I hope that I was able to impart some knowledge into this. That's all from me. Thank you.
Thanks, Alvin. That's really interesting. Has anyone got any questions they want to ask? I don't see any questions in the chat. Oh yeah, Xiaojin has raised their hand. Do you want to ask your question? And Jaya's got a question as well. So go with Xiaojin. Oh, they've lowered their hand now. Jaya, do you want to ask your question?
Yeah. So when you showed the projections for different SSPs, what we evidently could see that SSP 5 is quite away from the other three. What is the possible reasoning that you found with the analysis uh, associated with it?
You muted, Alvin.
Thank you. So thank you, Jaya, for your question. So this is also consistent with the GCAM input. So this is just confirmation of what is fed into our model, because this is a global average value of this QF. This also comes from the GCAM model. So if you do a quick search about these SSPs and energy consumptions, they will also fall in the same line. And this comes with the narrative or the storyline behind these shared socioeconomic pathways. And I think SSP5 is not a really sustainable future, which led to that. I'm not the expert of the SSP here, but there's a storyline behind this. Regional rivalry, I guess, if my memory is correct, about this SSP5 that results to this amount. So when you say regional rivalry, the country is more invested on not working with another country, so they need to protect themselves, and thereby they need to use a lot of energy on their own. If my understanding, if my memory is
Yeah.
correct with that, there's a storyline
Thank
behind
you.
it. Yeah, but thank you for your question.